In the previous videos, we learned how to compose functions. We also learned about the structures like magma, semigroup, and monoid, which lets us to combine values. As a matter of fact, functional programming is all about combining things. We break problems into smaller but well-defined pieces and then compose and combine them. In this video, we will learn about how to compose functors. Let's start with a simple function. IsEven receives an integer and returns a boolean indicating if the input is even or not. We learned that functors wrap types and functions and map them to new ones. In our example, the isEven function is mapped to f of isEven, and the integer and boolean types are mapped to f of those types. A good example for functors can be option. Option maps all types and functions and bring them into a context in which we have a concept of an absence of a value. But specifically for mapping functions in functional programming, we use a function named map or fmap. And this map function is specific for each functor. Let's consider another functor like list. What I want to talk about in this video is, can we take two functors, like option and list, combine them and create a brand new functor, like composed? The composed functor, similar to option and list, maps types and functions to new ones. What we're really looking for is to find something like this circle operator that not only can compose option and list, but it can compose any two functors. The first question comes to mind is, how does this composed functor behave? Does it behave like both f1 and f2? And if so, what does that even mean for example, option and list? In order to understand this, let's look at the definition of functor. Functor only has one method named map that receives a function from a to b and converts that to a function that receives f of a and returns f of b. Well, we already know that this is not a valid TypeScript syntax. In the previous videos, we learned how to get around TypeScript limitations by introducing HKT interfaces. But in functional programming, these are unnecessary details. The essence of what we need can be encoded like this. As you see, in order to find a general definition for composition of functors, the only tool we have in our disposal is the map method, which is simply a function. In other words, the composition of functors seems to heavily rely on composition of their map functions. And the good news is, we already know how to compose functions. In order to see this better, let's look at this from the category perspective. Considering our familiar isEven function, list functor maps types and functions from the first category to the second one. We already know that in functional programming, we are dealing with a single category. However, to visualize things more clearly, let's imagine these circles as separate categories for now. Next, let's try to map the second category using the option functor. As you see, in the third category, everything is wrapped with option around the list. By looking at this, can we come up with arrows, aka mappings, directly from the first category to the third category? If we can, it means we could find a composition definition for our functors list and option. For objects, this is pretty simple. From each object or type, only one arrow goes out. So we only need to follow that arrow and connect the objects from the first category to the third one. The definition of composing functors for types here is simply nesting the types and type constructors. Like for example, our new functor maps integer to option of list of integer directly. What about mapping functions? Can we do the same as what we did with types? Well, although mapping between categories are not generally functions, In functional programming, map of list and map of option are actually functions. This looks pretty familiar, isn't it? It's a function consuming the output of the previous function. You guessed this right. This is a function composition. You can even see this in the resulting function. And this mapping is not tied to any specific function, but is abstracted and works on all functions in our categories. Honestly, in order to completely prove that this way of composing functors leads to a new functor, we need to check for functor identity and composition laws. But for the sake of the length of this video, I leave that to enthusiastic folks to look into that. So we could find a general way to compose any two functors and create a new functor. The new functor maps types and functions from the first category to the third one. Some examples can be composing list and option, option and list, either a string and option, either a string and list and either a string, or simply any two functors. Can you see the power functors and functor composition brings to us? Since this is general for any two functors in functional programming, many functional languages support this natively. We can always code a new functor definition for our nested structures. But the whole point of coding functionally is to modularize, reuse, and compose existing pieces. In order to see where does this come useful, let's look at an example. Tail is a function that receives a list of integers and returns the tail of that list. For example, if we have a list like this, the tail function ignores the head of the list and returns the tail part of it. This works well, except for one case. What happens if the list value is nil? Or in other words, the list is empty? Then what our tail function should return? There is no value representing our need. The tail of the list is absent, and we don't want our function to be partial. I think by what we learned so far, you already have some ideas on how to fix this. We can simply return the option of the resulting type. Let's name our function safeTail, meaning it is safely returning the tail. Now we can implement our new function. First, we pattern match on the inputs. In case of nil, we return none. Otherwise, we return some of the tail of the list. And optionally, we can cancel XS from both sides, representing it in 0.34. What we're returning is the nesting of option and list. And this way of nesting always leads to a new mappable structure. Well, we found a way to compose functors, but not all concepts and type classes are composable. For example, in future lessons, we will learn about monads. But unlike functors, not every two pairs of monads compose. In order to compose them, we need to introduce new concepts like monad transformers, but more on that later. In the next video, we will look into functor composition in practice. Till then, thank you for watching this video. Please like and subscribe, and I will see you in the next one.